we've gone through and we've identified what the formulas are for the forward, backward, and center difference for the second derivative numerically. So now let's take an example that we did earlier and let's extend it now to the second derivative. And so what we're going to do is we're going to go ahead and we're going to consider a function, the same function we did at the point x sub naught equals 2 that we did before. And this time we're going to do the exact same stuff we did before, except we're going to do it with the second derivative. So, and as you might remember in the first video, we utilized both h equals 0.01 and h equals 0.001. And then we just basically cut and paste and changed a few things. So it's really not so bad once we program one of them correctly. And again, our formulas are up here. Okay, so let's keep these three formulas in mind as we go through and try to find out what our approximations are at the second derivative. So first thing we're going to do, let's take some sims and we're going to do f and x. So we're going to have a function of f in terms of x, and f is going to be equal to our x raised to the sine of x. All right, so done with that. And let's get the actual value. So for the second derivative, I'm going to say deriv is going to be equal to diff f comma x comma 2, right? For the second derivative, we have this third parameter 2. And then finally, we're going to say that the actual value is going to be equal to, when we substitute back into deriv, the old variable is x, the new variable or the new value is going to be the value 2. All right, so that should give us the actual value. And just to get an appreciation of what the second derivative looks like, I'm going to run this and you all can see how complicated this thing is. All right, so imagine trying to do that by hand. Doesn't look like a lot of fun. All right, so we have that. Now let's go ahead and numerically try to find the second derivative. I'm going to define two h's. I'm going to define h1 to be 0.1. I'm going to define h2 to be 0.001. All right, and the reason I'm doing that is just because, well, in the problem, that's what it tells me to do, right? 0.1, 0.001. And then we have the x naught, which is 2. All right, so I'm going to define x naught to be equal to 2. And now let's define our first forward difference. Okay, so I'm going to call this f diff 1. And again, our formula is going to be 2 steps minus 1 step minus the original function over h squared. And then we're going to subtract 2 of those first steps in the middle. All right, so that's going to be when we substitute into f, the old value is x, and the new value is 2 steps ahead. So that's going to be x naught plus 2 h's, or 2h1 in this case. Now we're going to subtract 2 of the exact same thing, except it's going to be 1 step. So this is going to be, instead of h or 2h1, it's just going to be h1. And then finally, this one is just going to be the function evaluated at the value with no steps, x sub I. And then we're going to divide that by h squared. All right, and that's going to give us the approximation. All right, so I'm just going to execute that. And it's not really going to mean much to us because, and it should be h1 there, I apologize. All right, so let's try that again. Again, this isn't going to mean much to us because unless we're a supercomputer, we don't know what that is off the top of our heads. So let's just copy and paste this. And I'm going to make f diff 2. And I'm going to do the exact same thing that we did before, where we're just going to change all the h1s to h2. All right. Now what we can do is we get the error. I'm going to call this forward error 1 or fair 1. And that's going to be equal to the absolute value of f diff 1 minus the actual. And then we're going to divide that by actual. All right. Now, if I run this, all right, this is our f error. All right. So again, we don't know what that is yet, but we'll see in a moment. We're going to do the same thing for f error 2. And we're just going to change that to 2. And finally, we're going to do an fprintf, where we're going to print out our actual value. We're going to print out the step size. We're going to print out the forward difference, approx, and then finally we're going to print out the error. And it's actually should be percent error. And so I should probably multiply these by 100 to get to the percent error. All right. And we're going to /n. And last thing we're going to do is we are going to print out both. All right, so fprintf. I'm going to print out a %f for the actual, a %f for the step size, a %f for the forward difference approximation, the second derivative, and a %f for the error. And the parameters that I'm going to call are going to be the actual, and we're going to call out the step size, which is h1 in this case, and the f difference, which is going to be fdiff1, and then finally the error, which is going to be fair1. And I'm going to do the exact same thing. And remember, once we get this, then we're good, because all we have to do is just change a few things. So we just set up the first one. All right, so, and then just to make sure that next time that we're ready, I'm going to do 2 entries so that way we're good to go. All right, so let's see what we get out of this. All right, now I want you to notice the percent error. Okay, I'm going to fix the top part, but we have negatives for the percent error, and that's probably because the denominator should have an absolute value. So I'm just going to put an absolute value in the denominator to ensure that we get a relative absolute value or a relative error in that. All right, and then also I'm going to fix this a little bit. All right, so let's see if that works. All right, there we go. If I really want to be picky, I'll do 2 more entries here. But so what we have is we have that with 0.01, we have about 6% error, or sorry, with 0.1, we have about 6% error. And then with 0.001, the second derivative is almost negligible with respect to the error. So we have 0.09% error. All right, now we're going to do the exact same thing, except we're just going to do it for the backwards formula. All right, so we still have all this the same. Now I'm going to change all of these F's to D's, or B's, excuse me, for backwards error. Right, and then our formula is a little bit different, because remember what we're going to do is we're going to start with x0, and then we're going to subtract h1, and then we're going to subtract 2 times h1. Right, so that's really the only difference, is that we're just going to change these a little bit. The ordering starts at 0, and then you go back, and then you go back again. All right, and if you don't believe me, just look at the formula. All right, our formula says we start at the x sub I, and then we work our way backwards. With this one, we start at the x sub I, and we work our way forward. All right, I'm going to cut and paste this. I'm going to change that to bdiff2. And the only other thing I'm going to have to do is just change all of the h's to h1s to h2. All right. And I'm going to change this fdiff to bdiff. And then finally, I'm going to change this fdiff to a bdiff. Not that that matters with the code. And then I'm going to change this to a B, this to a B, and then these 2 to B's, and we should be good. All right. So let's see what happens when we execute the backwards difference for this. All right. Now the backwards difference has a little bit more error. All right, not much, but enough to where it's almost double the initial type. All right. And then right here, when we start increasing the step size, then it starts to become really, really close. Okay, so in this case, it looks like that the forward difference would give us a much better approximation than the backwards difference. But remember in the last video, we saw that the center difference gave a far superior to either approximation to either the forward or backward. All right, so let's change this to center difference. And we're going to change this to center difference. And we're going to change this, and we're going to change this. All right. Our formula, a little bit different, but not much. All right, so if we look at the formula for the center difference, 1, and then I, and then -1. All right, so it still follows that 1, -2, 1 pattern divided by h squared, except we're not going up 2 steps. Okay, so for the first C difference, we're going to have x sub naught plus h1. And then we're just going to have -2 fx sub naught. And then we're going to have x sub naught minus h1. All right, and then we'll do the same thing down here, except now it's going to be h2s. And this will be plus h2. All right. Down here, I'm going to change this to center difference or C diff. Let's change this to C diff. So we're getting close to the end of this, by the way. So just hang tight, almost there. Now let's see what type of error we get out of this. All right, so we're going to execute. All right, and as we expected, the center difference gives us a far superior value than what we've been looking at with the backward and the forward difference. So really cool how the center difference almost always, at least for the problems that we're doing, gives us a really good estimate as compared to the other two. Now, the last thing that we're asked to do is we're asked to create one last table, right? And from our instructions, we are asked to produce the table displaying the display at all 3 methods at the lowest step size possible, which is 0.001 that we use, and the percent error. Okay, so all we're going to do is let's just go ahead and we're going to have our fprintf. All right, and literally what we can do is we can just go ahead and say we're going to have 6 inputs for this. So we are going to have, let's say, the backwards difference, and let me make sure. Yep, all 3 methods with the percent error. Okay, so that's going to be our backwards difference, and then our backwards percent error. And I think we started with our forward difference. So let's have our forward difference and our forward percent error. And then I'm just going to copy this. All right, and copy it again. I'll just change this to the central or the center. This is the center, and this is the back, and this is the back. All right, /n. And we are going to have 6 inputs in our fprintf. All right, so we're going to have %f, and we're just going to have to guesstimate this. All right, so our first fdiff was fdiff2. All right, so that was our forward difference. So remember, we always use the second one to represent the h at 0.001, and then we had fair2. Right? And then we could literally just copy this twice and close it out. And we could just change this to backward and backward and center and center. All right, so let's see how far off we are with respect to our spacing, etc. All right, so we're probably going to need a little bit more spacing out of this. And this is the tedious part, just doing the spacing. All right, so let's run it again, see if we got any closer or further. A little bit better. Last time might do it. Close enough. Okay. And so what we notice is that the forward percent error is close to the backwards percent error, so it's almost negligible, the difference between those. However, the central percent error is much, much more superior. In fact, almost there's no error in that. All right, so good news is now we can approximate the second derivative utilizing this formula. And remember the actual value. Let's take a look again one last time at what the actual value was. I'll execute this and just run it, because this is the real beauty of it, is that trying to do this by hand is pretty taxing, okay? And I think that the method that we showed before, this wouldn't be so awful to try to do by hand because it's just numerical. We throw it in our calculators and be able to execute it. All right, in the next video, we're going to start taking a look at how we derive even better approximations. All right, so in other words, what if we just wanted to use a smaller 8 or an h that wasn't all that small, but still be able to get a reasonably good approximation? So we're going to improve our algorithms in the next videos.